We have the pleasure and the honor. Really, I don't know if you realize the person that you have in these 2 days here. Please make the maximum note to this course, because here we have the director of the National Laboratory for Fusion. So Joaquín Sánchez, Dr. Joaquín Sánchez is the maximum authority in Spain about fusion. That's the presentation. A long career in plasma for magnetic fusion. And now he is the representative of Spain in Eurofusion. He was the chairman of the board of Fusion for Energy, if I am not wrong. But actually you belong to the board in the committee in the Fusion for Energy, that maybe you know. If not, I said you that is the organization of the European Union or the Europe that manage the funding that Europe is investing in ITER. So all the funding of Europe going to ITER, not directly in ITER, but through Europe goes in Fusion for Energy, which is in Barcelona. He is a member of the board. He was the chairman of the board and the maximum authority of national fusion activities in Spain, including, and that's a very good point for him, including that he also push and support very much the activities that we have in inertial fusion, even that he cannot take all the decisions, but he always supports also the activities in inertial fusion. So thank you very much, Joaquín, for coming, and please, the floor is yours.
Thank you for your generous presentation. I in fact the maximum political authority, but not necessarily scientific authority in fusion in Spain. Yeah. And okay, so you already had this talk, in fact, was scheduled for yesterday, but due to an agenda problem of Ángel Ibarra, who is today in Granada, I volunteered to do it on the second day. It's a kind of introduction, so you already learned about the problem of materials, you learn about the problem of the breathing blanket in magnetic fusion, and you were given a nice overview talk by Carlos Alejandre, which I was listening on the streaming. So today I'm coming to fill some holes and maybe to repeat a few things. Yeah. So I'm not sure this is my. Okay, I would like to start here. Yeah. So this is a DT magnetic confinement fusion plant. Essentially, it's a thermal plant. You have a source of heat which produces steam, goes to the generators, turbines, electricity. Yeah? What is the raw material? Deuterium, lithium, essentially. What do you burn here? Deuterium and tritium, which is obtained from the lithium. What is the exhaust? The exhaust is essentially helium. Helium poses no danger to persons, no danger to the environment. It doesn't accumulate. Yeah? It's even valuable for industry. You would not want to go to send the helium to the atmosphere. You want to keep it and to use it. Yeah? So it's essentially safe. So it's fusion energy safe, friendly to the environment, massive, very important. We are not speaking of providing some megawatts, even a few gigawatts. We are proposing a solution which will change the energy paradigm. Yeah? We will convert what is energy today on something like internet bandwidth. You don't say, oh, there is a shortage of internet bandwidth. I cannot use so many gigabytes anymore. No, I mean, you use gigabytes, a kind of flat rate. So we want to give flat rate for energy from the economic and, very important, environmental point of view. So that a lot of things that today we have a problem of energy, but there are a number of things that we might need and that we are not even thinking of, like massive water desalination, massive production of food, massive recycling of raw materials, which demands a tremendous amount of energy. So massive is very important. We will not provide a few megawatts hour. We will provide terawatts hour. And the fuel is abundant, inexhaustible for a million years. In fact, because you need very little of this fuel. Just with a glass of heavy water and a battery of an old telephone, you have the energy for the next 30 years. And when you have the energy, it's not your electricity bill, it's the energy in your car, the energy in your heating system, and the energy you use every day when you move, buy food, or use any service. Yeah? So that looks very nice. So where is the problem? Why don't we use this? The problem is there. Yeah? We say, oh, there is a fusion reaction, you get some heat, nice. Yeah. This fusion reaction has an advantage. It's very difficult to reach. And this is one of the reasons why it's so safe. So this, as soon as something doesn't work, the first thing which happens is that you lose your reaction. And also, for those people which might not believe that the physics works in that way, think on something much simpler. Your fuel is not inside, like in a nuclear reactor of the ones you have today. In a nuclear reactor of today's, your fuel for the next, I don't know, weeks, maybe months, is inside. If you lose control, Fukushima, the fuel is inside. You cannot get there and solve the problem. Here, my fuel is outside. So if you don't believe the physics and you think, oh, there might be a problem, think that you only have inside your reactor the fuel for the next 10 seconds. If you cut the fuel, no reaction anymore. Yeah. Okay, so the problem comes from the fact that we need those particles. In order to get fusion, particles need to get very close, very, very, very close. And those particles are charged particles. Yeah? And there is an electrostatic repulsion, very strong. Yeah? And you need, once the particles are close enough, the nuclear forces will enter, those are attractive, and you will get fusion. But you need really to send one particle against the other at a very high energy, so that this can happen. And this happens through the famous tunnel effect, because the 1/r in your electrostatic force is so big that if you wouldn't have the tunnel effect, you will never get there. Yeah? So we say you have to accelerate particles at high energy. Maybe people are thinking on giga electron volts. High energy here is not so high. You remember, proton, boron, we were told very high energy, 600 keV. This is nothing, I mean. We will accelerate at 15, 20 keV. I always say, in a high school, if you take some care, you could do it. Yes? This is just accelerate a particle with 15 kilovolts. The problem is not to accelerate particles. And in fact, you can buy a fusion generator to generate neutrons for other applications at an affordable cost. The problem is that we want fusion to generate energy. And this is a completely different business. And one of the reasons is that we are working with Coulombian interactions. Imagine those would be just billiard balls. If you launch with this trajectory the ball, it will hit the other. It's just a matter of yes, taking the direction properly, yes. But those are not just billiard balls, those are charged particles. That means from very far away apart, they are feeling that there is another one. And they start moving away. So the fact that you are having a very good direction here will not help you. The particle will go away very easily. That means a very, very high fraction of the particles you launch will miss the target. So if you accelerate particles, only a few of them will really generate fusion. Yeah? Another interesting element that I will use later, so think about it now, is that in Colombian interactions, the fast particles have very light collisions, very low exchange of energy. Why? Because if this particle is very fast, the time which spends close to the other is very short. And therefore, the exchange of energy is very small. So fast particles have lower collision rate. They collide much less. Yes. Okay, so we need energy gain. What would be the solution? The solution would be, okay, if we accelerate the particles and we manage to have them on a container so that they are bouncing back and forth all the time, then sooner or later they will collide and generate fusion. Yeah? And the good thing is that when they generate fusion, they generate with deuterium, tritium, an alpha particle that will bring energy to the system. So you have the possibility to have ignition. I will come back about this concept of ignition that we have been already informed about. Yeah? So, but now imagine, okay, a container with particles as 15 keV. Doesn't look too complicated. But what is the parameter that describes you a beam of particles, the energy? What is the parameter which describes to you a gas of particles, temperature? And what is the temperature of a gas where all the particles are at 20 keV? At 20 keV, you have to multiply by 1 eV is 11,000 degrees Celsius. So you are talking about 220 million degrees for this gas that you have generated with your high school equipment. Yeah? 15 keV, 170 million degrees. This is the problem. What kind of container can we use for that? Yeah? So there is no container which survives those temperatures. Or conversely, if you manage by cooling that the container survives, then it will be your gas that doesn't survive at high temperature. So one or the other. Yeah? So when you have this problem, there are two solutions. One is inertial fusion, and you have been explained how this works. And the other one is, okay, let's look for a non-material insulator, good insulator, that keeps the wall cold and the plasma hot. And this insulator has to be non-material. There is no material which withstands the energy. Okay, we are going to take advantage of one thing, yeah, which is this high temperature gas is in the state of plasma. What is the difference between a plasma and a gas? Essentially, a plasma is a fully ionized gas with some other properties which I don't need to bring now to the discussion. And you will notice two things, which is if you apply a magnetic field to the gas, an electric field, for example, there's no current. Nothing happens because ions would like to go one way, electrons the other way, but they are attached like couples in the dancing room, yeah? And there will be no movement. The same with magnetic fields. They will not feel the magnetic field because the field which the ion and the electron suffer compensates. When you have this, if you put an electric field, electrons will go one way, ions will go the other way, there is current. And if you put a magnetic field, electrons and ions will feel it differently, but they are not attached anymore. They will feel the magnetic field. Yeah? And this is what we are going to take advantage of. In a plasma state, particles see magnetic field, can be affected by magnetic fields. So, how does the magnetic field confine things? Yeah? Last time I gave this talk, I made a joke, which is, for a physicist, for a normal citizen, it's more easy to understand that a magnetic field traps iron than a magnetic field confines particles. For a physicist, it's just the opposite. For us, it's more difficult to understand how a magnet works than to understand what happens to a charged particle, because the picture is simple. This is the Lorentz law. I'm not going to use many expressions. This is a very simple one, and it's probably one of the few ones I will use. The Lorentz law tells you the force that a charged particle undergoes under magnetic field. And this is a vector product, which means the force is perpendicular to the field and perpendicular to the velocity. That's very important. When you have a force which is always perpendicular to the velocity, that means the particle cannot be accelerated. I mean, the velocity will not increase. So you cannot give energy with a magnetic field to the particles. What you do is you bend the trajectory. Yeah? So the magnetic field will bend ions one way, electrons the other way, the trajectories. And this will be a circle. Yeah? What is the radius of this circle? The radius is the Larmor radius. It's very intuitive. If you have a high mass, this centrifugal force will make the radius larger. If you have a strong V, the force is strong, the centrifugal the radius will be smaller. So this is essentially the radius. If we are speaking about big fields, 1 Tesla is, if you have undergone a magnetic resonance image diagnosis, you have been inside a few Tesla machine, yeah? 1 Tesla and very small particles, electrons, protons, then the radius can be a few millimeters. For example, in a plasma, in ether, 5 Teslas and something like 20 keV for the ions will have a Larmor radius of about 2 centimeters. And what happens is the particle moves along the field line freely, but they cannot move perpendicular to the field line. They are kind of inserted in the field lines. So it's like cars in a motorway that can move forward and backward, but they cannot change track. Yeah? This is the way to trap particles, because if we now make it circular, particles will be all the time making those circles there. And this is what we do in a tokamak. Yeah? There is an element of further complexity in the tokamak. I'm going to courageously try to explain it to you because it's non-trivial. Okay, we have said a magnetic field makes particles to be trapped, making helices along the field lines. Now, if I bend the field line, this will be a closed thing, and life will be easy. Not so easy, because if you have a magnetic field made with circular coils, one after the other, if the field lines will be straight and everything will be nice. If you now make a car wheel, yeah, a donuts, a torus, inside things will be compressed and outside expanded. This is very graphical. And this will generate a gradient in the magnetic field. There is no way to have a torus with a constant magnetic field. There's always more magnetic field inside and outside. And then the particles, which are making things like this, they have a longer radius outside because the field is smaller, and a shorter radius inside because the field is bigger. And they are not anymore making this, but they are making this. They move. The result is a little bit more complicated. Particles go out if you just have a donuts with a field, simple field inside. You need the field to be twisted. Yeah? There are many examples in daily life where you see that twisting things solves a problem. For example, if you have the jam jar and you put some jam, you do like this. With the wine also, people do like this. The people who work with fused glass also have the fused glass, and they are all the time turning, so it's something which plays a similar role. So you need a magnetic field which is twisted. And that's why you need this complex tokamak, not just coils in the easy way, yeah? Okay, so now we have learned how to confine particles. Nice, yeah? This is the largest tokamak in the world today, yet the joint European torus. I think Carlos Alejandro yesterday was showing to you some pictures as well. You see, this is 4.2 meters inside. This is where the deuterium-tritium experiments with gain 0.6 were run in 1997. And this year, 2021, we are going to do another DT experiment. I think it's next week, so maybe there will be in a few weeks, yeah? So working with deuterium in fusion is expensive. With tritium. Tritium is expensive. And because tritium is radioactive, you have to change completely the way of working in the machine. All the systems have to be prepared for that. So working with tritium is something that you do not do every day, because you have the advantage that more or less the same physics with very minor changes you can obtain with deuterium only. That's why most of the fusion experiments in magnetic confinement are done only with deuterium. And just a few experiments from time to time to really test if fusion happens were done with tritium. Yes? And as Carlos Alejandro, I think he was showing yesterday, the experiments in JET in 1997 were showing up to 16 megawatts of fusion power. And this is what the target now in the experiments in the coming weeks is to reach the same level, but in a much longer pulse, because the 16 megawatts were transient. I will explain later to you why, because a lot of material from the wall was coming to the plasma. Now JET has installed a different wall, more difficult to use, but more stable. Yeah. So it seems that we have a solution to the problem. That's why 60 years ago people say, oh, this will be a matter of a few years, and we will have fusion. So is the magnetic confinement perfect? Of course, we don't want particles which stay forever without colliding with anything, because we will not have fusion. So we need collisions. And if you have collisions, you have track displacements. When you have a collision, the particle will move inwards or outwards with the same probability. It doesn't mean the particles can go in or out when they collide. But this is a basic law of physics. When you have random jumps, at the end there is a transport from the place you have more to the place where you have less. So particles tend to flatten the density distribution or the temperature distribution with their random movements. Yeah? And how big is the jump? The jump is typically 1 Larmor radius, yeah? So just a few centimeters. And this confinement time here, I will come back to it in another slide, so I don't discuss it now. With this picture, people say, okay, how fast would the particles go? If this would be the single mechanism, we could have fusion in machines of this size. Yeah? We might have other problems, yeah? But from the point of view of confinement, a relatively small machine could do the job. The problem is that the plasma is turbulent. And turbulence changes completely the picture. Yeah. Where is this turbulence coming from? Always when you have an energy gradient, you have source for micro instabilities that grow and become instabilities. This idea, I can give you a few graphic ideas of what an instability is. I mean, I don't know, maybe, you know, supermarket charts. Very frequently, if you try to run with the chart, you will get an instability in the wheels. It will start to vibrate and will not run anymore. Yeah. If you put a piece of paper outside of the car, if you go fast, there is in principle no force to make it to move, but it moves because of turbulent instabilities. So instabilities in systems take energy. I mean, are phenomena which amplify oscillations, essentially. So instead of having the static resistance to the force, the system starts moving, the movement amplifiers, and you get a lot of problems. I mean, you can use it for making music, but usually they give you problems. Yeah? And this is a simulation of what instabilities do in a plasma. Yeah? And then the jump is not anymore the Larmor radius. The jump is typically of the size of those structures. This could be those codes could mean different densities in your plasma, yeah? And then the transport is much faster. Yeah? In order to measure this transport, we define a parameter, which is the confinement time. The confinement time is the time where the energy goes 1 over E, so more or less to 1/3. Yeah? And you can define confinement time for a magnetic fusion plasma or for a room. For example, if we are in winter, this room, we put some heating system, outside is 0 degrees, inside is maybe 18 degrees. We switch off the heating, we measure time. When the temperature goes from 18 to 6, 1/3 of the difference, this will be the confinement time of this room under those conditions. What are the parameters which govern the confinement time? Geometry, insulation, and very important, size. Small things confine energy much worse than big things. It's like animals in nature. The big animals have problems with cooling. The small animals have problems with retaining the energy. Yeah? So this is because of the surface to volume ratio. As soon as you become bigger and bigger, your volume to surface becomes larger, because surface goes with r squared and volume with r to the power of 3. Yeah? So size is very important. A few parameters concerning magnetic fusion, yeah? This Q, this is the fusion gain in magnetic fusion, not in inertial, is different, which is the fusion power divided by the power I need to inject to keep the temperature high. So if I have my container, my tokamak, I need to, in order to increase the temperature of the plasma, I need to put energy in. How do I do this? I can do it by ohmic heating, which is just the resistance of the plasma inside the tokamak. I can inject radio frequency. You know, the particles are making those wheels. If I put radio frequency at the same frequency, the particles will get more and more energy, and by collisions, give the energy to the others. And I can just inject fast particles. I can accelerate particles outside and inject them inside, with the problem that you cannot accelerate particles if they are not charged, and you cannot inject particles if they are charged. So you have to get charged particles, accelerate, then go through a neutralizer, a tricky thing, and then the particles go in. So you spend energy to heat your plasma, and your plasma, because magnetic confinement is not perfect, will lose this energy. At a given moment, you will reach high temperature, you will get fusion, and what you want is that you get as much fusion at least as heating. This is Q equals 1, what we call break-even, which is just a psychological point. There is no physics on this. Yeah? You get as much as you, okay. This is very important, ignition. This is when the plasma generates fusion, the alpha particles. You remember D plus T equals neutron plus alpha. The alpha particles hit the plasma, and then you switch off your neutral beams, your radio frequency, and the plasma burns by itself. This is our concept of ignition. And to get there, this gentleman and others after him established a criterion, which is, okay, what are the conditions to get a plasma where the energy from fusion is bigger than the losses? Yeah? So that I don't need any more to put heating. So you need enough particles and density. Enough particles so that they collide. You need T, some temperature, because at low temperatures, no fusion. And you need, important, confinement time. Because if we lose the energy very quickly, then no matter how much I generate, it will go out. So if you get this to be 3 times 10 to 21, you will get ignition. Yeah, and here you have many experiments along the last 50 years moving slowly towards the ignition condition. Yeah? Every experiment has a name because it's much easier to give a name. It's like the Apollo 11 or whatever, than to see the machine that was built in such city in 1925 and so on. So it's easier to give names, and you see how they progress towards the goal. One important element which I was missing is this one. Transport generates trouble. Transport makes our machines more expensive, as you will understand, but we need it. Because again, magnetic fusion is not inertial fusion. In inertial fusion, you make your shot, you get your energy, you clean, and you put the next one. In magnetic fusion, you have a system where you are burning deuterium, tritium, and you are generating helium. What happens to the helium? There is no shot, shot, shot. This is a continuous. Yeah? So the helium is there. You need to take it out. How do you do it? You do it I use the example of the refreshing of the air in an airplane. If you are in an airplane full of people, people are generating CO2, and the atmosphere in the airplane is getting less oxygen and more CO2. What do the engineers do? They just take air out all the time and put in fresh air all the time. That means they do not extract the CO2, they extract everything, and they refill with fresh air. Yeah? So we need to do the same in fusion. We do not extract helium, we extract everything. And we fill in deuterium and tritium. And then we will, this helium, separate from the deuterium and tritium in the fuel system. I guess yesterday I didn't see the full talk of David Rapisarda, but maybe he was speaking about blankets and about fuel system as well. Yeah? So there is a system that separates helium. But for this you need transport. If the particles don't go out, you will just get more and more and more helium, and then your reaction will fade. Yeah? Okay. So I was saying, you need so the thing is difficult. You have transport. We are 40 years away of all the time of fusion. Why is this so difficult? Okay, if you need to get, in order to get this confinement, because getting density and temperature is not so difficult with your heating systems. That the confinement is the tricky thing. Yeah. Getting this confinement is difficult. How can I improve the confinement? What are the limits to the confinement? Magnetic field. The magnetic field cannot be infinite. We estimate that the limit is 10 Tesla. Beyond 10 Tesla, you have essentially two problems. One is the superconductors do not work. Now there are high temperature superconductors which are not so sensitive to the magnetic field and could work at higher intensities of field. And the other problem is the forces. I mean, if you have coils on a tokamak, when you energize the coils, they would like to be as apart from the other as possible and as straight as possible. And the forces go with the magnetic field square, essentially. So the forces become very large. And your coils are made of terms that will compress one against the other. And you might very easily break the insulation between one layer and the next one. So it's not easy to go beyond 10 Tesla. What is the other thing? In a room, if your insulator is at the limit, what is the next thing you can do to keep energy? Size. You can play with the size. And we do. We estimate that in order to get ignition, you need 1,000 cubic meters of plasma. Imagine the first tokamak at the end of the 60s was 1 cubic meter, 0.3 kV. 20 years or 30 years after, yet 100 cubic meters, up to 30 kV, at least the electrons, maybe the ions not so much. 16 megawatt of fusion power, yeah? Maybe in 2021 we will get more fusion power, yeah? So this is a huge size scaling, and high technology plus big size is a recipe for tremendous investments and developing times. Yeah? So in order to get there, we have ITER. ITER is a machine which is, I think, nearly those 1,000 cubic meters of plasma. Yeah? It's a big development with a lot of complexity. Look that even the building is part of the experiment itself. And this building, which has been constructed in a consortium with Ferrovial, yeah, is a big challenge from the point of view of civil engineering. Yeah? And ITER will have two objectives. I don't spend too much time on describing ITER because Carlos did it yesterday, but we will get Q equals 10 for 500 seconds to demonstrate fusion gain, and Q larger than 5 for nearly half an hour to demonstrate the sustainability of this reaction. Yeah. In addition, there will be technology tests on materials, tritium generation, the test blanket modules, and so on. It's a big undertaking, as Dimitri was telling us, about 25 billions, and it's a joint effort of more than half the mankind. Those countries, yes, involve more than half mankind. Yeah. 25 billion euros. This is a lot of money, but think about, the world uses nearly 90 million oil barrels every day. Multiply times $70, and you will get that this is just a few days of the cost of oil that we are burning. And we are burning, it took many million years to generate the oil, and now we are burning it in about 200 years. No oil anymore, yeah? So the people who come after us, they will say, oh, those guys in the 21st century, they burned all the oil, didn't give us anything. So let's spend at least a few days of oil to give them something. Yeah? Why Q equals 10? Q is bigger when you have a bigger machine, which means more expensive. When ITER was approved by all those governments, they didn't want to spend freely billions and billions. So the designers had to give them a machine that could be paid, but that at least would be meaningful from the point of view of the physics. So is Q equal 10 meaningful? Yes. Why? Look, one of the big questions in magnetic fusion is ignition possible at all? Why? Because in order to get ignition, we want to use the alpha particles. The alpha particles which are generated in the fusion reactor, we say, oh, those alpha particles will hit the plasma for us. Yeah? But look, I told you the Larmor radius for an ion at 20 keV is something like 2 centimeters. That means the diameter of this circle is 4 centimeters for an ion, deuterium, for example, yeah, in ITER. What is the Larmor radius for an alpha particle? The Larmor radius goes with the square root of temperature, of energy, more or less. So an alpha particle is born at 4.3 MeV. Approximately is 250 times the energy of the 2 centimeter Larmor radius ion. What is the Larmor radius? Is square root of 250, something like 16. Yeah? So the radius is 16 times bigger. So instead of a radius like this, diameter like this, we will have a diameter like this. And if you have the alpha particles doing those kind of circles, they will get out very quickly. So are those alphas going to hit our plasma, or are they going to be lost immediately? In addition, I told you, fast particles collide less. Remember? Because they pass very quickly, there is no time for pushing the other, and those particles are very fast. So in addition to the big thing, the probability that they give the energy to the other is smaller. Yeah? So people started doing calculations and they say, okay, they will do the job. And it is going to demonstrate it, hopefully. And in order to demonstrate it, we need a plasma where the main heating system is the alphas. And look, if you have Q equals 10, because the alphas have 20% of the energy, we have Q alpha equals 2. Yeah? So in ITER, the alphas will hit twice more than the rest of the systems. So if the alpha hitting exists, we will for sure see it. In fact, there are some experiments in the 1997 JET DT shots that kind of show that the alphas were hitting the plasma. But this is very important. That's Q equals 10 is important. Q equals 10 means the alphas will be the main hitting system. Yeah. Okay, it is a very complicated technology and political experiment. Look, everybody, I mean, in order to convince so many countries to spend their money on a source of energy that will give results in 20 or 30 years from now, so that the people who vote you next year will not benefit from this, was not so easy. So they were more interested in the technology development, or they were very interested in the technology side. And they wanted to participate on everything in the cake. So they didn't want to let Europeans and Americans and Japanese to do the nice things, and they only do the simple things. So everybody wanted to work in the big magnets. Everybody wanted to provide superconductors. Everybody wanted to participate. And you see so many flags in many of the systems. Yeah? This means a very complicated integration. You have another international experiment, the CERN. In CERN, the in-kind contributions are just modular systems, the diagnostics. But the CERN machine is built by the CERN central team. Yeah? Here, the components are built by the countries and provided to ITER. Just to give you one example, the US contribution is this. Imagine, so it's like it interferes with everything. So it's not the US are providing this element or that element. The US, and the same for the others, but I took this because it was provided by our American colleagues and it's very graphical. You see, every country will provide in kind, that means they will build at home and bring it and install an absolutely integrated set of systems. Yeah? This is, no need to look to the detail, just see the overall picture. Yeah? So this means things go slow. In ITER, we had extra costs and extra time. And this is because of many reasons, but one of the reasons is in-kind contributions are complex, and also are complex because sometimes you have a conflict of interest. This is the typical conflict of interest where the guy who says what he wants doesn't pay for it. Yeah? So ITER say, I need this coil. Then Europe says, okay, here you have the coil, and say, oh, guy, I need a better coil. I need a Rolls-Royce coil. And the Europeans say, oh, it's okay, a Renault coil. Yeah? So, and then there is a discussion, and the ITER engineers demonstrate that they need a very good coil, and European engineers come back and demonstrate that the simpler one does the job, and discussions, delays. This is just, we didn't have the problem with the coils, but we had problem, for example, with the buildings. Yeah? Today, the so-called first plasma is scheduled for the end of 2026. Very likely it will go slip a little bit, but it's important to keep, I mean, in a complex project, if nobody believes that the schedule is meaningful, then everybody relaxes because say, oh, but those guys with the coils are slow, so no problem for me, for my system. So people need to say, okay, the date is 2026. Don't think that the vacuum vessel will be delayed and you will have more time. And therefore, maybe next year there will be a rebaselining of the project and give 1 more year or 1.5 more year. But today is 2026, yeah, for all the systems. But the high fusion power experiments will require, it's expected, 10 more years. So we are speaking about, I mean, some of the people in this room, the youngest ones, might be the session leaders of the DT experiments in ITER. Yeah. Is ITER the end of the story? Not really. I mean, I don't know if Angel was showing this picture of the roadmap to locate dones, but this is the roadmap of magnetic fusion seen by Europe. Yeah, so we are doing ITER, we are designing demo, and in parallel we need to solve the problem of materials. We are working on the accelerator as a backup solution. We are an accelerator laboratory, CMAT, but I'm not speaking so much about accelerators, maybe a few words afterwards. And also there is a lot of activity in improving, improving safety, improving cost, and projections of how future power plants will look like. Yeah. So in order to reach this, the next step is, after ITER, is demo. What are the difference between ITER and demo? The main difference is ITER has fusion gain. ITER as a plasma provides 10 times the energy, but not as a plant. ITER doesn't even have a turbine. So the ITER facility will not generate 10 times the energy. It's the plasma as a physics system, very important. Demo as a facility will provide energy. The idea is the European demo will provide something like 300, 500 electric megawatts in the network. The original demo was 1 gigawatt. We have, in order to be more, to come earlier, we have decreased some of the conditions. ITER will buy the tritium from the Canadian nuclear power system. Demo will generate its own tritium. There is no tritium in the world to keep demo operating if they wouldn't have a breeding system. ITER is going to use standard, it is called ITER grade stainless steel. It's a low cobalt stainless steel, but relatively standard. Demo will use reduced activating materials. Today it's Eurofer. Yeah? The point is how clean this Eurofer will be, we still don't know. Because in order to be really low activation, it has to be an extremely clean Eurofer. Yeah? We will have long pulse operation. Originally, the idea was, okay, 24 hours a day, 7 days a week. Now we are thinking, okay, maybe just so many hours a day, some hours a day, but not 24 times 7. And important, when the goal is ahead in time, far ahead, all the countries go hand by hand. But once people will see that fusion is around the horizon, maybe their interest depart. And today, there is a Chinese demo project, there is a Korean demo project, and there is a European demo project. Yeah? And we don't know if demo will be like ITER, a joint project. Maybe it is not. So, what is the, within the European roadmap, what are the kind of problems, what we call the missions, to reach demo? Look, there is the materials we discussed yesterday. Number 4, tritium self-sufficiency, discussed yesterday. Elements like improving safety, we are working with tritium, important, improving safety. No problem, fusion requires a safety treatment because we are using dangerous substances, not because we are a nuclear reactor. very important. The fact that fusion reactor has fusion reactions is irrelevant, more or less, concerning safety. For example, the cooling system today is not which is the key system in nuclear power stations, is not an issue in ITER. Yeah? You can just lose all your cooling and nothing essentially will happen. Yeah. But I want to discuss more the red circles, which are more physics related. Yeah? The plasma regimes of operation. This is a job for ITER. This is essentially what ITER will do. ITER will improve the confinement so that demo can reach this high Q. The big Q in demo will be around 40. We don't want to reach ignition. Why? Because a system in ignition is very difficult to regulate. I mean, you don't have your accelerator if the system runs by itself. Yeah? So we prefer to operate at a high Q, but not extremely high. Typically Q equals 50. That means we can regulate the power in a more refined way. Look, if you have ignition, the only way to control the power is by injecting more or less fuel, like in your car, the accelerator. But the reaction time is very slow, so you inject fuel and the system reacts maybe 20 seconds after. This is too long. If you keep the need for a little bit of radio frequency, giving a small fraction of heating, the system reacts in a few seconds. So we prefer to use as accelerator a heating system than the gas. That's why we will work in demo at Q equals 50 and not trying to get Q equals infinite. Yeah? Another important element is going from the Q equals 10 of ITER to the Q equals 50 is not a job of a factor of 5. It's very quick. I mean, once you are in Q equals 10, you can move upwards very quickly just by changing your parameters. Yeah? So this will be done in ITER. The stellarator is an intrinsic steady-state reactor. I didn't discuss some of the problems of tokamaks that the stellarator will solve. Therefore, I cannot explain to you those advantages. But let's take it that the stellarator is more stable. So if you do just a few units, it's better to do a tokamak. But if you do many units, that means the cost of a more complex design is distributed in many units. It's better a stellarator because the operation is simpler. Yeah? So it's more difficult to construct, more difficult to engineer, but cheaper to operate somehow. Yeah? The stellarator is something in the future. Now, I want to spend my time now on this problem. This is, if somebody will tell you, what are the problems in magnetic fusion to reach demo after ITER? I mean, if ITER is successful, we demonstrate ignition, that ignition is possible, we demonstrate that fusion is feasible, we demonstrate the scientific feasibility of fusion. Now, what do we need what are the challenges for demo? We need materials, and with Eurofair, the thing could be done. We need a blanket. This is a very complex thing, but engineering and physics might solve it. We need a little bit better confinement. This is what we expect to get from standard development, reasonable progress of the development in ITER. Where is the real showstopper today? Here. And that's why I'm going to spend some time here. The heat exhaust. Yeah. What does it mean? Let me go here. Okay. Imagine this is a tokamak, you have your plasma, and you have your power. 80% of the power goes to the neutrons, and 20% of the power to the alpha particles. Professor Batani was explaining to us, oh, it's wonderful when everything goes to the charged particles and there is no neutrons. It depends. Look, the neutrons will give us some problems, the problems that Dr. Ibarra explained yesterday. But from the point of view of taking them out, the problem is relatively mild, because the neutrons escape isotropically, and the neutrons are absorbed in volume. So when a neutron reaches the wall, not every neutron will give the energy there. Most of neutrons will go in, and they will give the energy in different depths. Or most of them will reach the blanket and release the energy where they are expected to do, in the blanket. Yeah? So the neutrons are not really a problem of energy exhaust. But what happens with the other 20%, the alpha particles? I mean, the alpha particles are there, they are confined, but sooner or later they will move outwards and they will reach the wall. Yeah? What happens when they reach the wall? And I will say, oh, look, but you told us your wall is not a problem because you have magnetic confinement. Look, what I told you is I need to separate the very hot part of the plasma, the part that cannot be, that I have to keep hot, from the wall. But the particles that reach the wall are not the very hot ones. So the center of the plasma is very hot. Here I have fusion. The edge of the plasma, the temperature goes down. It's not so hot, but it's hot enough to be a problem. The edge of the plasma is at a temperature of typically maybe 500,000 degrees. Very high temperature. But you have one advantage. You can manage to cool it without affecting the inside. So I can, let's say, kill the temperature in the edge. I cannot kill the temperature in the center because then I will have no fusion. But I can afford to cool the edge of the plasma. So in the edge, I just care that the wall doesn't vaporize. Yeah? So those, typically in a 1 gigawatt reactor, those 200 megawatts of alphas have to reach the wall, and I have to manage somehow. And the problem with the alphas, differently to the neutrons, is that they release the energy in the surface. They do not penetrate and distribute their energies. All the energy gets in the surface. And this is a serious problem. Why? What is the worst problem with this? Because you say, okay, you cool your wall, you manage, maybe you have to exchange it after a few years. The problem is not only that one. This is a part which is more important, which is the particles which reach the wall, they do two things. One thing is they hit the wall, which I can try to solve by cooling. But they do another much worse thing, which is there's the direct extraction of materials by a phenomenon called sputtering. So if a fast particle hits the wall, they might extract a piece of the wall. And this piece of the wall goes inside. Yeah? So we need to avoid this impurity migration towards the plasma. And why? Why are impurities so bad? 5 minutos. Yeah. I calculate, I say, oh, I have only 37 view graphs, so take it easy. But, okay, why is this so bad? Because when the plasma loses the energy in the form of light, the magnetic field cannot solve it. So we can keep the particles, we cannot keep photons. And the emission of photons goes with the C of your material squared. That means if you have iron, one iron ion generates 600 times more light emission than one hydrogen. And this also goes with temperature, which is a problem when you want to do fusion at high temperatures, yeah? Like proton boron. But So we need to avoid, by all means, that high C elements from the wall go inside the plasma. And in order to avoid this, now I have to accelerate, we invented the divertor. Look, when you have a limiter, I mean, the particles are inside, they are moving inside, and this is symbolic. They are slowly going out. The plasma is rotating, so that's why I make a kind of spiral. So the particles don't go like this, but they go slowly. So at a given moment, they will go out. When they hit the wall, if they extract material, the material, which are neutral atoms, they do not see the magnetic field, they go straight, and they penetrate and give us a lot of trouble. We invented the divertor, I mean the physicist, which is the particle does the same thing, but instead of going to the wall, at a given moment, it's like in a motorway, you get an exit. And this exit ends on a piece of metal where the particles hit. They also extract material, but this material is far away from the plasma. And also it has to go against the main flux. So it suffers a lot of collisions. In addition, here in the divertor, you generate high pressure. And this high pressure is very good for the pumps which are extracting material. Those pumps which are all the time taking the gas out in order to to extract the helium. So the divertor is a very clever solution. And all the tokamaks, ITER, demo will have a divertor. Problem, all those 200 megawatts go in a very thin ribbon there. It generates a lot of heat in these plates, and they can be easily destroyed. Now we don't have the problem of particles going to the plasma, but we have the problems that our plates will last for a week. So we need to work there. And there are many solutions. So this is so limiters, divertors, how do they look? They also have this, always have this geometry. And this is how the wall of ITER will look like. In this area where the thermal loads are smaller, you will have the famous beryllium with chromium zirconium plates, which there is a Spanish consortium who is building a number of those elements. Yeah? The divertor will be tungsten. Originally it was carbon, but now it was decided that carbon is a problem and will be tungsten. This is one idea that the British are developing, the Super X divertor, in order to increase the area where all the energy goes. So instead of a thin ribbon, you get a much thicker one. There is also another idea which is called the snowflake, which this was developed in Swiss and didn't get too big results. Yeah. There is also one possibility, which is, okay, if we manage to generate a lot of light here, so we cool those ions by making them to radiate. How do we do this? Injecting gas, argon, krypton, neon, at the plasma here, far away from the hot region. So we get a lot of radiation there. We can get up to 70 to 80% of all the energy which goes out to be cooled in the way of radiation. And this radiation is, again, very well distributed, no problem. Yeah? This is another possibility. Because I don't have much time, I will not discuss this, but okay, what are the options? Carbon fiber composites, which is already discarded, tungsten, beryllium, but beryllium also gives problem, and liquid materials. Liquid walls are a very clever solution because they are self-healing, so it's not easy to destroy, a liquid wall. Yeah, but it can be free liquid, which is very complicated, or liquid on a mesh. Yeah? And here you have some examples. Yeah? And this liquid can be lithium or tin. And you need other technologies. Essentially, you need reliability of the system, the famous reliability, availability, maintainability, inspectability, RAMI. Yeah? You need other conventional technologies like helium to water exchangers. You need to take care of the helium. If you use a lot of helium, much more than the one you generate, by the way, you might have a problem with helium supply. And the helium comes from the same place where petrol comes, where oil comes. So we don't want to replace the oil dependence with another dependence. With the time, this will be very important, high temperature superconductors. And of course, we need, if fusion costs 10 times than other energies, it will not fly. Yeah, so this is also important. Alternative fuels. I don't think already we learn a lot about proton boron, which is, I was saying, the holy grail inside the holy grail, yeah, the proton boron. And also the deuterium helium-3, which has the peculiarity that you need the moon mining, and this was the fundamental of several movies. Yeah? Moon mines to get helium-3 and the fusion energy. We don't really think this will be feasible on a reasonable time scale. And there is another one, which is the fusion-fission hybrid. The Russians like this very much, yeah? Which is, okay, with a Q equals 5, or maybe even a little bit less, and a fission gain of 10 in the right blanket, you get a Q equals 50 with today's technology. So the good thing of this is that the fusion reactor that you need for this, we know how to do it today. Q equals 5 machine is relatively trivial. Yeah? So advantages, much simpler fusion core. You can use it for waste burning, avoids uranium scarcity. It's safe, because if you switch off the fusion, the whole thing stops. And it's cheaper and faster than pure fusion. Yeah? The disadvantages, of course, yesterday, David Rapisarda explained to you how a blanket looks like. Imagine that this blanket, in addition, has to do another job, and not a simpler one, which is the fission reaction. Also, proliferation. Those machines are very nice places to produce all kinds of nuclear products. And as I was telling, the blanket is very complex. And the safety is also more complex. So some people say it has the good of one and the good of the other, or you can see it the other way around, say it has the bad of the fusion and the bad of the fission. Yeah. Okay, so I stop here. This is all, and I wait for your questions. Thank you.
Thank you very much, Joaquin. Really, I could stay for hours speaking year in, and what you are saying to us all in this presentation, Joaquin. You gave, I have so many comments about your about your talk, because they were great. For example, just for funny, I like this concept that you put. It's unmaterial container. That's great, no? It's beautiful, unmaterial container.
Yeah, yeah.
And the sample that he used it for getting the instabilities, just because of the manufacturing of the glass, is perfect. When you saw one people making a crystal, making this, and then comes the glow of the crystal, and they need starting all the time to move round and round, because if not, the crystal, the glass, wow, fall down. Great. Many questions. But I give the floor for the students. Thank you, really. Oh, very good, excellent. We have time for many questions. It doesn't matter if we arrive a little bit late to the lunch.
I have a question. Is there any reason why high temperature superconductors are not being used in ITER?
Yeah, the first main reason is they are not yet developed enough. So there is, to my knowledge, nowadays, not a single big coil built with high temperature supercomputers. There are ideas, they are smaller coils, but a big coil with high temperature supercomputers has not been developed. And ITER needs very large coils, and it's a very expensive project, so we do not want to risk that we use a non-well-proven technology. Look, that the coils of ITER are expensive, but they are just less than 10% of the cost of the project. Yeah.
Okay, thanks.
Okay, thank you very much indeed. It has been grateful, very great. Now, just a curiosity. I mean, in the future, you say that, well, for ITER, you will buy some tritium from Canada, from the CANDU, I guess.
Yes.
Technology. But I mean, in the long future, I mean, how this will be managed? Because when you need to start a fusion reactor, you need tritium. So all the time you will need to bring tritium from somewhere.
Yes.
So
I guess we will manage to be self-sufficient as a community. That means a new reactor will get the initial load of a few kilograms, I don't remember how much, it's just 1 or 2 kilograms, from another fusion reactor. So the breeder, you can adjust your breeder system to have a small surplus, not a big one, but you can have some surplus. So fusion power stations will be able to generate extra tritium.
extra for the others.
That can be used for the next one. So I guess if you are a Iberdrola and you have this, you will manage your tritium stock for the next ones. Yeah.
Okay, thank you.
No? Okay, so just let me make just a few comments and asking you something. So, for example, talking about the proton boron, well, you certainly know when you talk about you remark especially how to exhaust the energy in the case of charged particles. No? And I want to remind now, Joaquin, and you know also, that the people in the 70s and in the 80s imagine proton boron, I'm talking about the 70s and the 80s, just making a direct conversion in electrical energy.
Yes, MHD generators. Yeah.
Yeah. So, yes, the movement of the charged particle induce like a transformer, like an electrical transformer, the current in the second coil, you know? So movement of charged particle, that is a current. So what you have in a transformator, in a transformer, you have a current that induces a current in the secondary. That was the,
Yeah.
So that's the only way, really.
Yes, but I'm not really familiar with the details of those generators, but I don't know how those would work. First, with a fully thermal plasma, that means particles are not aligned, they are just moving in all possible directions. And in particular, on a tokamak, I don't think this would be possible. The people, 3 alpha, I don't know if 3 alpha, this company
Yes,
has
3 alpha.
changed name recently.
No,
But,
alpha.
but they had this idea of generating, they do proton boron, they generate 3 alphas, and they plan to get the energy through this kind of mechanism. But this is a linear device, so maybe there
Yes,
is
in that case, yes,
possible. Yeah.
it's perfectly possible. So you remark exactly the exhaust. Remember this, the exhaust is really key. And well, fission fusion, Joaquin, you remark the Russians the Russian demo is a fission fusion.
Yeah, they are.
So they are making research.
Yes, they
still.
are. Professor Belikov, I think, he was
Yes, Belikov.
the one who was pushing for this, and they still. And I think it's. I mean, if you are in a hurry to get energy and you manage to solve the issue of the blanket, then maybe it's a better solution than just
But
standard
you remark something
fission.
very critical, which is proliferation.
Yeah, I mean, for me, proliferation is the real problem of
Is the real problem.
nuclear
Yes.
fission.
Yes.
Because if fission becomes the standard, every single country in the world would like to have it and the right to have it.
Yeah.
And then, at a given moment, you see that as a country kind of disappears because there is an internal revolution or whatever, and then a number of people that you don't know even who they are, they have a nuclear power station.
My last question, Joaquin, for all the people and for me also, could you explain clearly which is the difference between the energy confinement time and the particle confinement time?
Yes, yeah. The point is, if all the particles are lost at the same speed, hot and not so hot particles, then they are the same. But it seems that fast and more energetic particles go out faster than low energy particles. So usually the energy goes away faster than the particles. I mean, the energy in joules goes faster than the particles in particles per cubic meter, because the fast particles are lost preferentially. Let's say that's why they are different.
Okay. So, any other question, comment also? No? Well, thank you very much, Joaquin.